Rainbows, the stuff of unicorns, fairies, and pots of gold. They hypnotize kids simply because they seem so incredibly unlikely. How can we possibly have a gigantic Technicolor arc suddenly appear that stretches across the sky, which then disappears as quickly as it arrived? No wonder it is linked to magic and dream worlds. But the physics that underpins rainbows is no less amazing. It makes sense to most of us. But to truly understand it, you have to know about refraction. So let's find some gold. This is Thing 4. In our rainbows, there are two phenomena being exhibited. We have refraction of light as it enters our raindrop, and then total internal reflection of the light within the water droplet before the light refracts back out the side of the droplet. Refraction of light is governed by Snell's law. N1 sine theta 1 equals N2 sine theta 2, where N1 is the refractive index of the initial material and theta 1 is the angle of incidence. N2 is the refractive index of the second material, and theta 2 is the angle of refraction. Internal reflection occurs if the angle of incidence that the light is striking the surface at is greater than the critical angle. Critical angle can be calculated using the equation n equals 1 over sine theta c, where n is the refractive index of the material the light is traveling through, and theta c is the critical angle. Let's look at a challenging example of the type of question you could be asked to show how these might apply these concepts. In this question, you are given a situation where, much like in our rainbow, light enters a material and refracts as it does so before reflecting internally. Part A asks us to calculate the refractive index of the glass sphere. From the question, we know that N1, which is air, will be equal to 1. The angle of incidence, theta 1, is 36 degrees, and the angle of refraction, theta 2, is 18 degrees. In this case, we will use Snell's law to calculate N2. If we substitute our values into N1 sine theta 1 equals N2 sine theta 2, we have 1 sine 36 equals N2 sine of 18, or sine of 36 divided by sine 18, which equals 1.9 to 3 significant figures. Part B asks us to find the critical angle of the glass. For this, we will use our second equation, n equals 1 over sine theta c. So 1.9 equals 1 over sine theta c, which can be arranged to theta c equals the inverse sine of 1 over 1.9, which gives us 31.8 degrees. So, the magic of adding light with a raindrop does not need to have unicorns or pots of gold as part of the story. Physics is enough. The physical principles that underpin our world are amazing and will blow your mind. When you understand what causes what and why rainbows work as they do, it is no less impressive. In fact, I would argue it makes for an even greater story. It also won't stop me from occasionally checking if there is indeed a pot of gold at the end of them. This was Think 4. Thanks for watching.